Hello everyone, thank you for watching our presentation. My name is Guo An. I'm a PhD student from Nanjing University in China, and today I will present our Easter 2022 paper on autonomous driving testing. Its title is LiRTest, Augmenting LiDAR point clouds for automated testing of autonomous driving systems. Our slides contain four parts. First, we talk about the background of our work. Then, we explain our approach, experimental settings, and experimental results. Finally, we provide a brief summary. The development of autonomous vehicles has achieved tremendous achievement over the past decade with the rapid improvement of artificial intelligence and sensor technology. The Society of Automotive Engineers proposed 6 levels of vehicle autonomy, with Level 0 being the lowest and Level 5 being the highest. Level 4 autonomous driving systems have the highest autonomy level among the systems in production today. Recent results demonstrate that autonomous vehicles have become very efficient in practice and have already driven millions of miles without any human intervention. However, such intelligent systems often demonstrate incorrect and unexpected corner case behaviors that can lead to a fatal collision when deployed in real-world environments. Various such real-world cases have already been reported. For instance, self-driving Uber killed a pedestrian in Arizona in 2018, and Tesla's self-driving vehicle rammed a truck directly in 2019. There is an urgent need to explore a better approach to effectively testing self-driving software. As a typical safety-critical intelligence software, autonomous driving systems use sensors such as LiDAR and camera to capture surrounding environmental information as input, and automatically complete different driving tasks by various functional components. LiDAR is one of the most critical sensors, which perceives the surrounding environment through distant measurements by transmitting lasers and processing laser returns. Besides, it provides highly accurate range measurements that enable reliable detection performance. Moreover, unlike the camera, it is not affected by light, which can function well at night. However, there are various challenges in testing LiDAR-based self-driving software. First, in the operating environment of autonomous driving system, the point clouds sensed by LiDAR may be affected by various environmental factors. Next, the testing process of modern autonomous driving systems heavily depends on the collected dataset because of the diverse environmental conditions. It requires many resource consumptions to collect point clouds and the different environmental factors. Finally, the manual labeling for point clouds is a laborious and time-consuming task that needs a massive workforce to manually examine the visualization results. In order to alleviate these problems, we design and implement a systematic LiDAR-based automated testing tool, namely LiRTest, for automatically testing object detection systems of self-driving cars and further retrain to improve them. Next, we will introduce it in detail. This is general framework of our work. As shown in figure, domain experts design physical and geometric models to simulate the properties of LiDAR and the different adverse weather conditions and linear mapping between point clouds, respectively. Then, the transformation operators are defined according to the model construction. Next, the developer selects point cloud seeds from real-world data, leverages the point cloud processing unit to identify and process them, and implements the mutation algorithm based on transformation operators. After that, the transformed test data can be generated to evaluate the robustness of the 3D object detection model of autonomous driving. Finally, we get test reports based on detection bounding boxes and give feedback on operator design. Besides, LiRTest can improve the model's AP by retraining with the transformed training data. We investigate 7 different realistic point cloud transformation operators. These transformations can be classified into two categories, FN and weather, and we implement several transformation operators for each category and integrate them into LiRTest. The detailed definition and design are as follows. In this paper, we designed 4 different types of affine transformation operators, including translation, rotation, scale, and symmetry. We list the transformation matrices for the 4 types in Table 1. Like 2D images, one can apply an affine transformation to a 3D point cloud matrix I by simply computing the dot product of I and the corresponding transformation matrix M subscript tran. Therefore, the transformed point cloud matrix can be represented as equation 1. Moreover, layer tests can simulate characteristics of adverse weather conditions. Then we introduce the common and specific characteristics. According to extensive research, we found that rainy, snowy, and foggy days have a commonality in the attenuation of point cloud data reflection intensity. During weather effects such as rain, snow, and fog, the LiDAR equation for a target at a distance of m from the sensor is represented as equation 2, where P subscript R is the power received by the LiDAR sensor. Considering the rainy, snowy, and foggy atmosphere to be a homogeneous, uniformly scattering medium, we can obtain the simplified LiDAR equation 3. Then, the relative sensor power P subscript n is given as equation 4, where W is the weather strength, A and B are empirical coefficients, and the fractional reduction lambda can be defined in terms of the relative intensity of the fraction as equation 5, where P subscript 0 is the reflected intensity in the absence of rain, snow, or fog. Substituting the model from equation 4, the fractional reduction for a given surface at a distance m can be modeled as equation 6. This slide is about the specific characteristics. Rain may have another two impacts on LiDAR. First, the number of detected points decreases due to scattering from rain droplets. Secondly, the presence of rain also introduces noise to the range measurement. For snow, we design a normal distribution function to simulate the point cloud noise of snowy weather, and we model the fog-specific characteristics pattern as a cylinder. A major challenge in testing the complex LiDAR-based autonomous vehicle system is to create the system's specification manually. Besides, the annotation of the 3D point clouds consumes a large amount of time. To avoid these issues, LiRTest is designed to realize the FN and weather metamorphic relationships for LiDAR-based autonomous driving systems. Note that the only difference between them lies in that the affine transformations require applying the corresponding operators gamma to obtain the correct labels for the augmented data, while weather transformations perceives the same labels before and after the transformation process. In order to make the metamorphic relationships more permissive, our equality criteria zeta is derived from average precision. To evaluate the performance of LiRTest, we choose four state-of-the-art models as the testing subjects in the experiment. Further, we use KT 3D object detection benchmarks. For research questions, we focus on the unique characteristics of each transformation operator and the effectiveness of LiRTest. Whenever the transformation operators is applied to original data, we randomly select the parameters for a specific transformation. Then, we employ the AP to measure the testing performance of LiRTest and use 40 recall positions to achieve a more fair comparison of the results. We compare the neurons activated by different synthetic point clouds generated from the same point clouds, and also compute the neural activation set dissimilarities between per point cloud transformation and the corresponding seed point cloud. We measure the dissimilarities by measuring their Jacob distance. Figure 2 presents the result for all possible pairs of point cloud seeds and transformations, and we also calculate the mean value of Jacob distance for each combine of model and operator to illustrate the dissimilarities from another perspective, as shown in Table 2. Figure 3 shows the result for all possible pair of transformations for different models. We found the transformed data triggered different DNN's internal logic in the 3D object detection model relative to the seed data. Besides, our experimental results indicate each transformation operator has unique characteristics and increase the diversity of the inputs. To prove the effectiveness of LiRTest in detecting erroneous behaviors, we intercepted some errors found by LiRTest. As shown in the figure, the first two rows and the last two rows are the errors detected by applying weather and affine transformation when the original data are pedestrian and vehicle respectively. Figure 4 presents the moderately difficulty results of RQ2, which show the AP difference of car, pedestrian, and cyclist of all models for the original and augmented test set. After analysis, we discovered that adverse weather plays a critical role in affecting LiDAR detection performance, and models are more prone to erroneous behaviors for weather transformation than affine transformation. Here, we check whether retraining the 3D object detection models with some of the synthetic point clouds generated by LiRTest helps in making the models more robust. We randomly select a small amount of data from mixed transformed point clouds to train for all configurations. Table 4 shows that LiRTest can improve the object detection precision by retraining with the generated data, and the degree of improvement is correlated with the original detection precision. In summary, we proposed and evaluated LiRTest, the first systematic and automated model testing tool for LiDAR-based autonomous vehicle. LiRTest innovatively designed 7 transformation operators. Specifically, LiRTest equips a physics-based model to simulate LiDAR point clouds for different weather conditions. We use autonomous driving domain-specific metamorphic relationships to find erroneous behaviors of the 3D object detection models without detailed specifications. The experimental results show that the transformed point clouds generated by LiRTest can improve object detection module robustness through retraining. We believe LiRTest is a critical step towards assuring the quality of LiDAR-based autonomous driving systems. That's all for our presentation. Thank you for your attention, and please feel free to ask questions.